You are welcome to this tutorial. This is the Math and Chem tutor. Let's go through Bayes' theorem and the law of total probability, starting with Bayes' theorem. So, Bayes' theorem. So, the theorem states that probability of A given B is equal to probability of B given A times probability of A divided by the probability of B. Now let's prove it. Proof. Now, this theorem is a modification of conditional probability. So we are going to pick everything from conditional law. So let's consider the first case. From probability of A given B conditionally, it's expressed as probability of A intersection B divided by probability of B. Now let's make this the subject. Let's make probability of the intersection the subject. So probability of A intersection B, from that expression will be given as probability of A given B times the probability of B. Let's call this question 1. So that's question 1. Let's consider this second case the other way around. From also probability of B given A. So this will be expressed as probability of B intersection A divided by the probability of A. Let's again make this the subject, the intersection. So probability of B intersection A will be expressed as probability of B given A times the probability of A. Now, let's try to call this equation 2. So this is equation 2. Now we know, but probability of A intersection B is always the same as probability of B intersection A. So that means equation 1 basically will be equal to equation 2. Equation 2. So we are going to equate the two expressions. So I will have probability of A given B, this expression here, so times the probability of B equaling this expression here. So that will be probability of B given A times the probability of A. Now making this term the subject, so I'll get probability of A given B is equal to probability of B given A times probability of A. Then we divide by the probability of B. This is what we are calling Bayes' theorem. So we shall use it later. Let's go and look at the law of total probability. So next, law of total probability. Law of total probability. Now let's dive into it. Let's state the law, but let's pick it from here. Consider sample space S with partitions B1, B2, etc. as many as possible, which are actually mutually exclusive, events. That means no two events can occur together. No two events can occur together. That's the meaning of mutually exclusive. And exhaustive. They are also exhaustive events, meaning they cover the entire sample space. They cover the entire sample space. Now, if there is another event A which is part of the sample space, if A is an event which occurs through B1, B2, etc., then probability of A, this is now the law, probability of A is equal to probability of A given B1 times probability of B1 plus probability of A given B2 then times probability of B2 plus as many as possible. So we can summatively say probability of A will actually be the sum from I is equal to 1 to n of probability of A given Bi, then times probability of Bi. Let's try to put more light. Now, in summary, we said Bayes' theorem, because now we want to use them in the calculation. Bayes' theorem was saying probability of A given B became probability of B given A times probability of A divided by probability of B. But now this law, the law of total probability saying probability of A, let's say A is depending on events B1 and B2. So probability of A will equal to probability of A given B1. We are only considering two events, B1 and B2, times probability of B1 plus probability of A given B2, then times the probability of B2. If what we mean by A occurs through B1, it's like if we are looking at determining the probability that a student passes math, we can consider two schools, B1 and B2. Then A will stand for the event that a student passes math. Then we can look at how he passes math based on school B1 and B2. Let's dive into examples. Now, in these two examples that we are going to do, we are going to be using both the theorems or the laws and also the tree diagram, since this can be done also using the tree diagram. Let's now look at this first example. Solution. A mobile phone dealer imports Nokia and Motorola phones in a given consignment. 0.5 were Nokia. So we are going to consider N, let N stand for Nokia phones. So probability of Nokia is 0.5. Then probability of Motorola is 0.45. Now they have said the probability that a Motorola phone is defective. So the defective is the event which is part of the sample space containing Nokia and Motorola. So defective is occurring through Nokia and through Motorola. So probability of defective given Nokia, then probability of defective given Motorola. So given Motorola is 6 out of 100, which is 0.06. Then this is 4 out of 100, which is 0.04. Now let's go to the first part of the question. Determine the probability that it is defective. So we are looking at Roman 1, defective. So we've said defective is occurring through Motorola and occurring through Nokia. So we are going to say probability of defective according now to the law of total probability, would be defective given Nokia times probability of Nokia, then plus defective given Motorola times the probability of Motorola. Let's substitute these values. Defective given Nokia is this value, so that is 0.04 times for Nokia is 0.5, then plus defective given Motorola is 0.06 times Motorola is 0.45. That gives us the answer as 0.047. Punching in the calculator. Let's look at Roman 2. So Roman 2, we are looking at a Motorola given defective. So probability of Motorola given defective. So here we are calling in by the theorem that will be defective given Motorola times Motorola divided by the probability of defective. The defective value is just down here. So we are going to substitute in defective given Motorola is actually this value. So I'm going to have 0.06 times probability of Motorola 0.45 divided by this answer here 0.047. That gives us 0.5745. So you try that in the calculator. Let's also use the tree diagram to see how we can do the same question using the tree diagram. Let's look at the tree diagram. So method 2, tree diagram. Tree diagram. So there are two phones. We have Nokia and we have Motorola. So either Nokia is defective or Nokia is not defective. Motorola is defective or not defective. We are using D for defective and D prime for not defective. So in the question, the probability of Nokia is 0.5. So this is 0.5. Then Motorola is 0.45. Then defective given Nokia is 4%, which is 0.04. So not defective given Nokia will be the balance 1 minus 0.04. That will give us 0.96. Then in the question, for defective given Motorola is 6%. So this is 0.06. Then the balance for not being defective would be 1 minus 0.06, giving us 0.94. 0.94. So this line will be N intersection D. This is N intersection D prime. This is M intersection D. This is M intersection D prime. Now, when I want probability of defective will be this line and this line. So this will be probability of N intersection D plus probability of M intersection D. So let's substitute those values. We take the whole line here. So that will be 0.5 times 0.04 plus also this line. So that is 0.45 times 0.06. That gave us 0.047. Now let's go to Roman 2. This is Roman 1. Roman 2 wants probability of Motorola given defective. Probability of Motorola given defective. We now apply the conditional law. We have forgotten the other two theorems in order to use a new method. So this is M intersection D divided by probability of D. So M intersection D is actually this line here. So that is 0.45. So divide by the defective value, which is right here. So that is 0.047, giving us 0.5745 as got earlier.